Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA is a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
Coming to work every day and being humbled by that.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
Hello and welcome to Voices from DARPA. I'm your host, Tim Haynes.
In case you don't recognize it, that is a Volkswagen Touareg coming into the finish line configuration. Ladies and gentlemen, boys and girls, it's been done. How about that?
We just heard the sounds of an autonomous vehicle named Stanley crossing the finish line to win DARPA's second off-road Grand Challenge back in 2005. It was one of 5 vehicles to successfully complete the 132-mile desert course without any human intervention. In the 20 years since, competitors from that challenge have helped establish the rapidly advancing self-driving car industry. Our guest today, Dr. Stuart Young, program manager in the Tactical Technology Office, was at the first Grand Challenge event in 2004, where there wasn't quite as much to cheer about.
I was actually in the desert as an engineer from the Army Research Lab for the first race with all the hype and hoopla and excitement. And, then things, as we know, didn't go so well on the first experiment. The farthest vehicle went about 7 miles, and there was a little bit of, melancholy about why did this, should have done better. But the thing about the environment is you can't predict the edge cases kind of by the definition. And I think it is a really great foreshadowing of the problem that I was interested in.
Stuart was at the Army Research Laboratory for 29 years, working on various programs, including several from DARPA.
Ran a division where we, started focusing on developing an internal research team focusing on field autonomy, off-road autonomy. Then I was invited to come to DARPA and try to work on that problem at the DARPA level, so I jumped at the chance. My career goal was always to be a DARPA program manager, so I'm super excited to be here.
Stuart joined the agency in early 2020, quickly developing a portfolio focused on advancing autonomy in multiple domains.
Once I got here, I was handed the ALIAS program to complete that program, which is Aircrew Labor in Cockpit Automation System, focusing on developing autonomy aids to improve safety and reduce cognitive burden of pilots on enduring aircraft. Some people call them legacy or older aircraft. And then the main thing I came to DARPA to do is create RACER.
RACER stands for Robotic Autonomy in Complex Environments with Resiliency.
We need to be able to travel fast on cross-country off-road terrain. We need to do that at a speed that is operationally relevant. So the bottom line is we have to do it fast and we have to do it reliably so that the warfighters can have it as a tool in their toolbox.
The program kicked off in late 2021. And at the time of this recording in spring of 2025, RACER is in its 5th big experiment, rigorously testing its algorithms on platforms in the real world. In case you haven't seen videos from RACER yet,
3,
we want you to be able to picture what Stuart is talking about.
2,
RACER is using 2 very different kinds of vehicles
1.
to test its autonomy algorithms.
Mark, go for auto. Copy, switching to autonomy.
The first is a 2-ton, 4-wheeled, all-terrain vehicle, a little bigger than a golf cart. The other is a 12-ton, 20-foot-long vehicle with 2 giant treads that looks like a tank. So imagine both of these vehicles tearing across deserts, up and down scrubby hills, swerving through forests, and tackling all kinds of other terrain at up to 30 miles an hour with nobody aboard. That's RACER in the field. We've been posting RACER video highlights since the first experiment. You can check out links in the show notes or visit the DARPA TV YouTube channel to see more. Now back to Stuart.
In RACER, we have no expectation that the trafficability of the terrain directly in front of us is navigable by the vehicle or not. And so constantly we have to evaluate that. And so that's computationally very expensive. We're doing it very close to the vehicle as well as far out as possible, which leads to the speeds that we can attain. That is not something that is static either. So you can imagine driving across a dry lake bed. It looks perfectly trafficable. It's dry dirt. Let's just drive. We can go really fast. And then it rains, and then holy cow, that dry lake bed is no longer a dry lake bed, and the trafficability of that same terrain that was beautiful a few hours ago or a few minutes ago is no longer trafficable. The reality is combat vehicles especially will have to maneuver in terrain that is highly complex off-road for tactical survivability reasons. In combat, the roads or terrain will obviously continue to be degraded through the activity of both sides. And so consequently, you have to deal with that. If roads are out or bridges are out, it's like, okay, well, then deal with it. So we have to have the flexibility to have our maneuver forces be able to drive wherever they need to, and we don't want them to be constrained to roads and trails. This is particularly important as we saw in, for example, the coin fight over the last 2 decades where IEDs were such a problem.
To clarify, a coin fight is a counterinsurgency fight where governments are trying to defeat rebellions. And an IED is an improvised explosive device, basically a bomb made from whatever random parts someone can get their hands on.
Well, the IEDs were always on the roads. Well, then don't drive on the roads, right? But that wasn't really the way we solved that problem. It provides you operational flexibility. It provides the ability to put more challenges for your adversary to prevent you from doing things. And quite frankly, that's where you can hide and give you that survivability that ultimately we think is important for the military.
Dr. Trent Mills is a colonel in the U.S. Army and is the Army advisor to the DARPA director. He's spent significant time and energy over the last few years engaging with the Army and other services to help accelerate understanding and adoption of autonomous capabilities.
We're open now to conversations like this, like, okay, well, what does autonomy really bring? We're not looking at autonomy as an option or as a tool in the toolbox. Let's sprinkle some autonomy. Or we don't think of it that way. We are appreciating how autonomy is going to change the paradigms. The very way we see warfare has to be seen through a lens of autonomy, not as an optional thing to plug in. And when you start to do that, and you do that all the way across the different warfighting functions of sustainment, of logistics, of communications, when you start to bring autonomy in as the thing you see the world through, you start coming up with better ideas. So it's an inspiring time. It's a really kind of optimistic time for DARPA to start unleashing these things because we're ready. We have a whole population of, I call them baby general officers, that have grown up through 20 years of this doesn't work, right? To now they're general officers. Now they're like, we got to do things differently, guys. We are not going to do that again. We don't think in single domains anymore, and we include cyber and space. So autonomy applies to everything. It's not just the secret sauce. It's, like I said at the very beginning, it's the paradigm through which we see the battlefield and the way to win. One of our more prominent 4-stars who runs Army Futures Command, for years he said, no blood on first contact. Because we know we're going to lose a lot of people, but not on the first contact. That's for the robots. And he'll say it just like that and say, you guys figure that out. You guys meaning the enterprise, all the smart people. The human domain is the Army. We're not platform specific. We arm the human. In the other services, we put humans in the machine. We wrap machines around humans. Because that's the primary weapon system, is the human being.
The first Grand Challenge was born with the intent to meet the warfighter needs, vehicles that can be driven without people in them to keep soldiers out of harm's way. The lessons learned from that first challenge continue to inform Stuart's work.
The problem with the world is there's an infinite number of edge cases, and so you can't deal with them until you discover them, and then you discover them sometimes catastrophically. So that was the thing I took away from the first one, and I was extremely motivated, like, okay, this is a pretty crazy, hard problem. And then fast forward to when I was pitching Racer, ironically, the director asked me the question, is like, well, I thought we solved this problem in the Grand Challenge. And I said, well, actually, we didn't. We solved a different problem. And so the Grand Challenge essentially was an oversimplification of the problem that we are trying to deal with in Racer. But it was a perfect motivating, and it took DARPA to motivate the industry to get started on that problem, which was more akin to taking advantage of structure in the environment and then solving the on-road driving problem. And also it exposed the fact that, hey, this off-road problem is actually a lot harder than we thought. Primarily the difference is the amount of a priori information and the structure in the environment. So in the self-driving approach, and even back in the original Grand Challenge, there was quite a bit of knowledge about the course that they were going to go on. So they had ways to essentially follow the yellow brick road, follow breadcrumbs along that trail and then basically stay on the trail. But they were essentially paralyzed if they would have to go off that trail. The part of the problem that Racer's dealing with, that is our norm. Like, our norm is to not be on trails.
The technology landscape has changed drastically since the Grand Challenge. Advances in compute power, sensor capabilities, and AI algorithms making Racer possible are the same trifecta advancing most of the tech landscape. What's setting Racer apart is its grounding in the physical world.
We realized we need more miles on vehicles, and it wasn't just putting miles on vehicles for the purpose of miles. It's miles on vehicles for the purposes of learning where the systems work, where the systems don't work, going after those edge cases I talked about earlier. I mean, these are off-road vehicles for a reason, and there's nobody on board. So we're only damaging metal and hardware. We can tend to be aggressive, and that was a paradigm shift that wasn't happening before. It's that aggressive nature, the ability to repair things quickly and have high cycle time in the field was another contributing factor in addition to the technology.
For as much as it's critical to get Racer going as many miles as possible, it might be somewhat counterintuitive to learn that this off-road autonomy program isn't focused on hardware development.
Racer is a software program. We're building autonomy stacks, we're building algorithms, we're building data sets, we're building models, neural network-based models. So the data gets used to train our models. There's manual tuning, which is not very scalable. So we have to develop labeling pipelines that are efficient. We also do self-supervising in our learning approaches. All of that together is essentially the autonomy stack that results in the system being able to execute driving the vehicle in that terrain.
Processing multiple sensor feeds through an autonomy stack to do real-time decision-making is incredibly resource-intensive. That's not a deal breaker for online AI tools like ChatGPT, where computing resources are virtually unlimited. But autonomous platforms have to use edge computing, which means they're limited to their own compute power and energy, so efficiency is critical. Racer platforms have to be capable of operating totally off the grid, in GPS and communications-denied environments, while still safely fulfilling their missions. We shared a high-level overview of the two Racer platforms earlier. Stuart's going to provide a few more details.
We set this program up that we wanted to test very aggressively and very hard, and so we needed a vehicle that would be reliable, and we tried to find one, and there really wasn't one that would do what we wanted to do, so we had to build it. We started with as much stock as we could, and then we tricked it out. We started with like a Polaris side-by-side 4-seater, which was very capable, and we were able to ruggedize all of our sensing and compute to be able to get after that. And that was really important for us evaluating the algorithms of our performer teams. And we were able to recover and quickly repair it when we were too aggressive, which was actually also a key component to the program, which is push hard, be aggressive. And when you have a problem, you learn from it and you fix the vehicle and then you keep moving on. We also put it on a tracked vehicle, which was a Textron M5, and that was to prove the agnostic nature of the autonomy to different types of platforms. So we go from a wheeled Ackerman steered vehicle to a large, heavy skid steer vehicle. And that transition to those different types of platforms, in theory, shouldn't affect the autonomy front end, like the perception and planning, but should only really affect the controls back end. We very quickly have the system running on that different style. Now that we've done that, it's critically important because we understand the nuance in transitioning to other type of vehicles. So I believe we truly are agnostic to the vehicles now. The Army, the Marines have interest in putting this on some of their program of record vehicles, and that is definitely not a barrier to the system. It's usually more of where can we put our sensors and the compute associated with it, but it's not about the vehicle. So the autonomy is generally applicable to any type of land vehicle.
The Racer program aims to not only be platform and payload agnostic, but also easily adaptable to any environment.
We've tested in 4 different terrain biomes. We've been to the desert, the Mojave Desert, so we've tested it at National Training Center at Fort Irwin, California, a couple times. So that area is replete with, obviously, rocks and sand. There's not a lot of vegetative, what we call different classes of semantic segmentation. It's basically rocks or sand and that kind of thing. It's not like brush and stuff that you got to go around. So it's very geometric in nature and the problem that you're trying to solve there. Then we've gone to places like Camp Roberts, California, which is Central Coast, California, which is obviously California is a big state, so still a very different biome. We've also gone to Fort Cavazos, Texas, which is hill country, Texas. It's a lot more deciduous, a lot more trees. The Central Coast also had trees and very significant V-ditches and elevating type of terrain. How much can we take the models that we build for one environment and move it to another, which is a key part of that resiliency that I was talking about. So we built models when we went to our 4th experiment at Fort Cavazos, Texas. That was the first time that we had been there. We did not build a model on that environment with any data from that environment by design. We wanted to see how bad our model would be. And the reality is it did pretty well right out of the box, which was a little bit surprising, but also gratifying. But it didn't take long for us to make some very small changes to our system, and then it performed much better. So that adaptation, how fast the systems can adapt, what's the manner of adaptation is something that we're really trying to understand. So the biomes that we've uncovered so far are not representative of all biomes in the world, but they are distinctly different, and that's been our goal, and we will continue to do that as we finish the program and go to some other types of vegetative environments, pine forests and that kind of thing.
As the RACER program has continued to push boundaries and tackle the next edge case, it's progressed through multiple phases and performer teams.
In phase 1 in the program, we had initially 3 performers. We had Carnegie Mellon University and a consortium they put together. We had the University of Washington, and we had the NASA Jet Propulsion Laboratory in Pasadena. We always had envisioned that we needed to not only prove this technology capability, but we also needed to provide a mechanism for the services to be able to buy this capability when it existed. And so working with the performer teams, 2 of them spun out companies. University of Washington spun out Overland AI, and Jet Propulsion Laboratory spun out a company, Field AI. Those companies are off and running, doing really well. The ability to transition this in a scalable way, universities aren't usually set up for that, so you really need industry to be involved so that the DoD and other dual use can take advantage of that. And so that has happened somewhat organically, although that was always a desired goal of the program to facilitate that. So I think there's a lot of disruptive energy that we're creating in showing what is possible, the state of the art, and then trying to show the operational evidence that this is actually ready to go, maybe earlier than they anticipated.
Colonel Mills weighs in with his perspective.
What the Army has learned from watching RACER and DARPA over the last several years, it's really kind of multifaceted. But the biggest success stories for me are how we've informed the requirements process. Warren, Michigan, where our folks that do kind of the autonomy integration into our ground vehicle systems, they are generating requirements documents that will drive acquisition, S&T procurement for the Army for the next several years. And a lot of the content of those really boring, dense documents are lessons learned from what RACER has revealed. There are lots of examples of how what RACER has done has shifted the appetite, shifted the ambition of the Army. And that's hard to do because the Army has a fight tonight. We can't wait. We have to fight now. So when we see it, when RACER proves something back in June and whatever, and here's the metrics, we're taking notes. The Army's like, oh, okay, we can do that now? Well, let's put that in the requirements document so then we can tell the acquisition community to go get that stuff because we know we just saw it. That signals my optimism is that I've seen the Army do it. I've seen the Army take it seriously. I've seen senior officers talk about it in an intelligent way, not just, we're going to do some autonomy. That was kind of par for the course even a few years ago. Now, our general officers are speaking in a way of they understand what autonomy stacks are. They understand what the network is going to require in order to support this thing, which is really making me optimistic about that going forward.
You might assume Stuart's taking a victory lap with RACER, but that's far from the case.
Just because you have a driver's license doesn't mean you can drive a tractor trailer or a motorcycle, right? The Department of Transportation, they give you, a license to drive those in special conditions. And so similarly, we have shown that we can drive in the conditions that we've tested it to, but we know there's other conditions that we still need to get after. So for example, driving at night, we need to do a better job of that. We've done it, but we can do better. So we are trying to drive the number of interventions down to 0, which means the autonomy has to get better for those edge cases so that when it encounters those edge cases, it either can deal with them or it can react more appropriately. So it could be the robot is just like looking at something and it doesn't know what to do and it needs help, or it may have crashed and flipped over or something like that. So clearly those are different degrees of intervention, and we do characterize those differently. It's a 2-hour recovery versus it's 2 seconds for a user operator to say, hey, back up and go around and do this. So it's really going after the adaptation of the system to other environments, and driving those interventions to 0 is where we're still focused on continuing to push on that. There's still a lot of meat left on that problem.
As our conversation comes to a close, we'll give the floor to Stuart for his thoughts on his experience at DARPA.
Coming to DARPA was something I obviously always wanted to do, and it has not for a minute disappointed. This is the greatest job in the government. It's the most stressful job in the government. But the beauty of it is it's all self-motivated stress, because I am empowered to solve a very complicated problem for national security. I'm given all the tools to do it, and I'm only limited by my time and my ideas and my team's ideas to solve that problem.
That's all for this episode of Voices from DARPA. For more information on Stuart Young and his programs, and for more racer videos, check the show notes or visit darpa.mil. As always, thanks for listening.